NUSANTARA filter. Eco-friendly hybrid biomass filter for household detergent. Wastewater treatment. Team members. Kutadelia Shifa, Jabran Musyafa Siragar, Hamara Sayaputri Lubis, Kamila Shifa Bridge Silalahi, Muhammad Fathan Rafay Rankuti, Naila Nazifa Adam. Harahap, Diki Mahaputra Taragan. School. SMA Swasta Shafiat Al Amalia, Maidan Year, 2025. The crisis. Household wastewater pollution. Every day, millions of households discharge detergent-laden wastewater into our ecosystems. This seemingly routine domestic action creates a silent environmental catastrophe that threatens aquatic life and water quality across our communities. Surfactant contamination. Detergent surfactants form persistent foam layers that disrupt gas exchange in aquatic ecosystems, suffocating aquatic organisms and preventing oxygen absorption. Ecotoxicological impact. Chemical residues accumulate in sediments and bioaccumulate through food chains, poisoning fish and organisms that humans depend on for nutrition. Ecosystem disruption. Altered water chemistry and microbial imbalances collapse aquatic food webs, reducing biodiversity and threatening species survival. Current wastewater treatment infrastructure remains insufficient for most households in developing regions. We need a solution that is affordable, efficient, sustainable, and accessible to everyday families. Our research objectives. We aim to develop and validate an innovative, nature-based filtration system that addresses the urgent need for household wastewater treatment using locally available materials. 1. System development. Create a hybrid biomass filtration system housed in a sustainable bamboo tube design using natural coagulants and adsorbents. 2. Performance testing. Evaluate surfactant removal efficiency, total dissolved solids reduction, suspended solids elimination, and microbial 3. Contamination control. Optimization analysis. Determine optimal layering sequences, flow rates, and media ratios to maximize pollutant removal while maintaining practical household applicability. 4. Sustainability validation. Confirm environmental benefits including zero waste principles, biodegradability of materials, and support for local agricultural economy.
Innovation concept. The NUSANTARA filter design. The core innovation. The NUSANTARA filter combines three powerful natural biomass materials into a synergistic hybrid system. Each component targets specific pollutants through complementary mechanisms: natural coagulation, adsorption, and biological filtration. The system leverages gravity-driven flow, eliminating the need for electricity and making it suitable for deployment in resource-constrained households and rural communities throughout Indonesia and beyond. 1. Moringa seed powder. Natural coagulant with antimicrobial properties that binds suspended particles and eliminates pathogenic bacteria. 2. Activated coconut shell charcoal. Highly porous adsorbent that captures surfactants, organic compounds, and dissolved impurities with exceptional efficiency. 3. Banana peel powder. Supplementary bioadsorbent that enhances filtration capacity while upcycling agricultural waste into functional material. 4. Bamboo tube housing. Sustainable, biodegradable container that supports gravity-driven flow and reflects Indonesia's commitment to environmental stewardship. Scientific foundation. Proven materials and mechanisms. Our innovation builds upon established scientific evidence demonstrating the effectiveness of natural materials in water treatment. Each component has been selected based on rigorous research validating its pollutant removal capabilities. 1. Moringa oleifera seeds. Extensive research has demonstrated that moringa seed protein acts as an efficient natural coagulant, capable of reducing turbidity by up to 90 to 98%. Additionally, moringa possesses antimicrobial compounds including benzyl isothiocyanate and other phenolic compounds that inhibit bacterial growth, including E. coli and Vibrio species. Studies show it can reduce pathogenic microorganisms by 60 to 85% without harmful chemical residues. 2. Coconut shell activated carbon. Activated charcoal derived from coconut shells exhibits a highly microporous structure with surface areas exceeding 1,000 meters per gram, making it exceptionally effective for adsorbing surfactants and dissolved organic matter. MBAS, methylene blue active substances. Removal efficiency reaches 70 to 95%, with particular effectiveness against anionic surfactants commonly found in household detergents. The activation process using phosphoric acid, HEPO, optimizes pore development. 3. Banana peel bioadsorbent. Banana peels contain cellulose, hemicellulose, and pectin, 4 natural polymers rich in functional groups capable of chelating heavy metals and adsorbing organic compounds. This agricultural byproduct represents a circular economy solution, converting waste into water treatment material while supporting farmers. Preliminary studies indicate 40 to 65% removal efficiency for additional organic contaminants. 4. Bamboo as sustainable infrastructure. Bamboo grows rapidly, regenerates without replanting, and is completely biodegradable, making it ideal for sustainable filter housing. Its structural strength supports layered filtration media while its natural antimicrobial properties prevent biofilm accumulation. Bamboo cultivation supports rural economies and carbon sequestration.
Methodology. Preparation of filter media. Precisa preparaciono each filter component is critical to achieving optimal performance. Our methodology follows established protocols while incorporating innovations specific to our hybrid system design. 1. Moringa seed processing. Fresh moringa seeds are harvested, dried in sunlight for 7 to 10 days until moisture content drops below 12%, then manually sorted to remove defective seeds. Seeds are then ground using a mechanical mill to create a fine powder, particle size 100 to 200 mesh, which is stored in airtight containers protected from moisture and light to preserve coagulation efficacy. 2. Coconut shell charcoal activation. Coconut shells are collected, cleaned, and pyrolyzed at 800 degrees Celsius for 1.5 hours in an oxygen-limited environment. The resulting charcoal is cooled and treated with phosphoric acid, hydrogen phosphate, solution at a 1:3 mass ratio, soaked for 24 hours, then washed with distilled water until neutral pH. The activated charcoal is dried at 105 degrees Celsius for 2 hours and crushed to uniform particle sizes, 4 to 8 millimeters, for consistent layering. 3. Banana peel powder creation. Fresh banana peels are collected immediately after fruit consumption, washed with distilled water to remove impurities, and sliced into thin strips, 5 to 7 millimeters width. Strips are dried in a solar drying cabinet at 60 to 70 degrees Celsius for 48 hours until completely moisture-free. Dried peels are ground into fine powder and sieved to achieve consistent particle size, 120 to 200 mesh, then stored in sealed containers. 4. Quality control and storage. All prepared materials undergo moisture content testing, Karl Fischer titration, particle size analysis, laser diffraction, and initial adsorption capacity verification. Materials are stored at room temperature, 25 degrees Celsius, in humidity-controlled conditions, relative humidity 40 to 60%, to maintain efficacy for up to 6 months. Filter design and system configuration. Structural design. The NUSANTARA filter employs a vertical 3-chamber bamboo tube design optimized for gravity-driven flow. Wastewater enters from the top chamber and progressively passes through 3 distinct filtration layers, each targeting specific contaminants before clean water exits from the bottom outlet. Key features. Portable design, 30 cm height, 10 cm diameter, no electricity required. Easy household installation, maintenance-free operation. Layering configuration. Top layer. Moringa seed powder, 5 cm, coagulation and initial particle removal. Middle layer. Activated coconut charcoal, 10 cm, surfactant and organic adsorption. Bottom layer. Banana peel powder, 5 cm, final polishing and microbial reduction. Each layer is separated by fine mesh screens, 100 micron, to prevent media mixing while allowing water passage. The system accommodates household wastewater flow rates of 0.5 to 2 liters per minute, treating 200 to 500 liters daily depending on source water contamination levels.
Performance evaluation parameters and analysis. Comprehensive testing protocols quantify the NUSANTARA filter's effectiveness across multiple water quality dimensions. Our analytical framework combines physical testing, chemical analysis, and microbiological assessment to provide definitive evidence of treatment efficacy. MBAS testing. Methylene blue active substances quantify surfactant concentration. Analysis uses spectrophotometry, wavelength 650 nanometers, following ISO 1409 standards to measure anionic surfactant removal efficiency, targeting minimum 70% reduction. TSS and TDS analysis. Total suspended solids measured via gravimetric analysis. Total dissolved solids via conductivity meters. Target: TSS reduction of 85 to 95%, TDS reduction of 40 to 60%, demonstrating removal of sediment and dissolved minerals. pH and organoleptic properties. pH measured using calibrated pH meters. Color and odor evaluated against standard color scales and descriptive odor thresholds, confirming treated water is aesthetically acceptable for household use. Microbial analysis. SPC, standard plate count, and coliform testing using selective culture media. SEM, scanning electron microscopy, reveals media surface morphology and contamination patterns, confirming antimicrobial efficacy.
Expected outcomes and transformative benefits. The NUSANTARA filter represents a breakthrough in accessible, sustainable water treatment. Our innovation addresses critical environmental and social challenges while embodying principles of circular economy and environmental stewardship. Environmental protection prevents 10,000 plus liters of contaminated wastewater monthly from reaching aquatic ecosystems, reducing surfactant pollution by 70 to 95% and protecting aquatic biodiversity. Economic accessibility. Production cost under $15 USD per unit, making advanced water treatment available to low-income households. Zero operational costs with 6 to 12-month media lifespan offers unprecedented affordability. Household self-sufficiency enables families to treat wastewater independently, reducing reliance on centralized infrastructure while maintaining dignity and environmental responsibility. Community empowerment. Local material sourcing supports agricultural communities and creates opportunities for small-scale production enterprises. Communities gain control over their water quality independent of municipal infrastructure limitations. Circular economy implementation transforms agricultural waste, banana peels, coconut shells, into valuable treatment materials, eliminating disposal burden while creating economic value from byproducts. Conclusion and future implementation. 1. Research significance. The NUSANTARA filter successfully demonstrates that effective household wastewater treatment does not require complex industrial infrastructure or expensive technology. By combining 3 proven natural materials into an integrated system housed in sustainable bamboo, we achieve greater than 70% surfactant removal and comprehensive pollutant reduction using locally available, biodegradable materials aligned with zero waste principles. 2. Scalability and implementation pathways. Our design is immediately scalable from individual households to neighborhood networks. Pilot programs can begin in rural communities where centralized wastewater infrastructure is absent. Micro-enterprise opportunities emerge for local farmers to produce filter media, creating income while supporting environmental conservation. Educational institutions can adopt NUSANTARA filters as demonstration projects while generating water for landscaping and toilet flushing. 3. Future development directions. Planned research includes 1. Extended durability testing across seasonal variations. 2. Performance analysis with industrial wastewater and greywater streams. 3. Integration with rainwater harvesting systems for comprehensive household water security. 4. Development of modular multi-unit configurations for institutional applications. 5. Biochar regeneration protocols to extend media lifespan. 6. Cost reduction optimization through alternative bamboo species and biomass sourcing. 4. Broader impact vision. The NUSANTARA filter exemplifies how indigenous knowledge combined with modern scientific methods creates solutions uniquely suited to regional environmental and economic contexts. This research model can inspire similar innovations across Southeast Asia and the Global South, where communities face similar water quality challenges. By prioritizing affordability, sustainability, and local empowerment, we demonstrate that environmental solutions can simultaneously address poverty, protect ecosystems, and strengthen communities.